Hello everybody, my name is Jonas Auder and on behalf of my colleagues Leon Busse, Ken Pfeuffer, Uwe Grünefeld, Radia Rivo, Florian Alt and Stefan Schnegers, I'm going to present I'm in Control transferring object ownership between remote users with haptic props in virtual reality. Virtual reality lets people collaborate remotely. For example, they can work on a creative task like designing a shoe. Together, they can combine their knowledge and skills to solve a task. In our approach, we explore how we can enhance remote collaboration using haptic props. This works as follows. In A, two collaborators meet at a virtual table. They are joining from remote locations. The objects they see in VR are mapped to haptic props to allow for natural interaction. This means they can just grab them and put them wherever they like with their hands. But they cannot move the objects from their collaborator because these are mapped to physical props located in a remote location. Therefore, we introduce another kind of haptic prop that allows for interaction with the remote objects. For example, in B, such a prop is used to transfer a remote virtual object to a local haptic prop. We implemented 3 different techniques to interact with remotely located objects in VR. Instructions, copy and cut. To initiate the interaction, one collaborator has to bring a local blank haptic prop close to a remote object. This can be used to create a visual instruction. The instruction connects the local object and the remote object. The local object can be placed to indicate the correct position to which the remote object has to be placed. The blank haptic prop can also be used to create a copy of the remote object. Now the copy can be placed correctly without the help of the remote collaborator. Like copy, one can cut a remote virtual object. Here, the virtual object is transferred to the local blank haptic prop. In this case, the remote virtual object turns to a blank haptic prop for the remote collaborator. To realize this, we developed our own collaborative distributed virtual reality environment. Our application allowed collaborators of each location to join and meet at a virtual table in the middle of a virtual room. The collaborators met at a virtual table measuring 80 × 80 centimeters. Our environment consisted of a simple room with white walls and a wooden floor clear of any distractions. At the table, the collaborators worked on a collaborative puzzle task. At each location, a collaborator sat at a real table in the middle of a tracking space. The virtual and physical tables matched exactly in size to prevent any mismatch. The collaborators sat across from each other during the collaborative task. As a task, we choose a circuit design scenario. The task resembled a puzzle task rather than a real circuit design scenario. We call this the puzzle task from now on. The objective for a pair of collaborators was to assemble a simplified and scaled-up circuit board consisting of microprocessor parts and corresponding circuit parts. One can see the circuit and microprocessor parts in the upper left. The required arrangement consists of 12 square components represented by 10 × 10 cm wooden pieces that we call the haptic props. One can see the final arrangement in the lower left. The task was designed to elicit collaboration. Each collaborator had half of the knowledge about the complete solution. Hence, to complete the task, the collaborators had to support each other by sharing knowledge. The collaborator in one location was provided with the plan showing the target positions of circuit parts, the other one with the target positions of microprocessors. One can see the individual plans on the lower right. In the beginning, each collaborator had 6 local parts, 3 of the type microprocessor and 3 of the type circuits. Hence, the collaborators could only place 3 of the 6 initial parts on their own and then had to collaborate to complete the arrangement. Further, they were provided with blank haptic props to allow for a remote interaction. This is how the plan looked in VR. Each collaborator could see the plan next to the virtual table. To interact with the remote objects, we implemented 4 different conditions. Creating visual instructions using blank haptic props, copying remote puzzle pieces using blank haptic props, cutting remote puzzle pieces using blank haptic props, and as a baseline condition, We used virtual reality with haptic props, but there was no interaction between local and remote haptic props possible. Through instructions, the collaborators could create a visual connection between blank haptic props and remote objects. Therefore, the collaborators used a blank haptic prop that could interact with the remotely located puzzle piece. The instruction indicated the correct position and orientation to the other collaborator. By following the instruction and placing the virtual object correctly, the puzzle piece was positioned correctly by the remote collaborator. By a copy, the collaborators could retrieve a copy of remote puzzle pieces using a blank haptic prop. The copy could then be placed correctly. If they ran out of blank haptic props, they could turn not needed puzzle pieces to a blank haptic prop using a specific deletion area. With cut, the collaborators could retrieve remote objects. They could use two blank haptic props to transfer a puzzle piece and then place it correctly according to their plan. As soon as the puzzle piece was transferred, the remote haptic prop turned into blank haptic prop. Finally, in the baseline condition, we provided no interaction technique that allowed to interact with remote objects. Here, the collaborators had to rely on speech and pointing to indicate the correct position of the puzzle pieces. We evaluated these 4 conditions in a user study. We recruited 12 participants, 6 female and 6 male, aged between 23 and 31. We asked participants to rate their experience with VR on a 7-point Likert scale. The participants stated that they have some experience with VR, with an average of 3.4. We formed groups of collaborators with these 12 participants. Each group of collaborators consisted of 1 participant and 1 confederate from our side. The confederate was instructed to act as a newly instructed participant and had no knowledge on the research questions. The participants did not know that they were collaborating with a confederate. The confederates adjusted to the working pace of the participants and did not make mistakes intentionally. Our study followed a within-subject design. Each participant collaborated in all 4 conditions. We balanced the conditions using Latin square. We analyzed the task completion times for each condition. Participants were slower in the instruction condition than in the baseline, the copy and the cut condition. For instruction, the average completion time was around 2.5 minutes. For the remaining conditions, between 80 to 90 seconds. Using instructions was significantly slower than all other conditions. We also measured the interaction duration for each haptic prop placement. The interaction duration was quite similar for the different conditions, at around 3 to 3.5 seconds per haptic prop placement. Here, we did not find any significant differences. Further, we measured the number of interactions with the haptic props. The number of interactions was highest for instructions. This is not that surprising because while using Instruct, the collaborators had to place 2 haptic props to indicate the correct position. First, one collaborator had to place 1 haptic prop to create an instruction, then the other collaborator had to place the corresponding puzzle piece according to the created instruction. Hence, we observe a higher number of interactions. Therefore, this result might depend on the design and technique rather than the collaboration performance. We asked the participants to specify the amount of verbal communication needed per condition on a 7-point Likert scale, 1 low amount and 7 high amount. The participants stated that they verbally communicated a lot for the baseline, with a mean of 6.33. Less verbal communication was needed when they used instructions, copy or cut. We observed the lowest verbal communication in the cut condition. Further, we gathered qualitative feedback from our participants. The participants reported that instructions were intuitive and easy to follow. Also, they enabled multitasking. For copy, participants reported that the collaboration was systematic and clear, but also confusing because there was a lot going on. For cut, some participants appreciated that they had not to wait for the collaborator and could continue by themselves. In the baseline condition, pointing was appreciated rather than verbally indicating the correct position of the puzzle pieces. We asked the participants about any strategies that they have developed over the course of the study. Several participants reported that they always placed those components that they had information about first. Then they turned their attention to their partner and the remaining components. For example, one participant considered the difficulty of describing a particular component's target position before deciding where to place components. By placing components on positions that would be more complicated to describe, this participant avoided a difficult description. To summarize our research, we explored haptic props for remote collaboration. Therefore, we introduced 3 collaboration techniques to interact with remotely located objects in virtual reality. We introduced instructions that can be created using haptic props in a virtual environment. These instructions help to communicate how a virtual object should be used or placed. We found that instructions reduced verbal communication and were easy to follow. Further, we introduced 2 techniques that allow to take over ownership of remote located objects. We introduced 2 techniques known from standard desktop environments, copy and cut. Through these techniques, the collaborators felt more decoupled from each other and could work individually. They did not have to wait for the other collaborator. That resulted in a lower task completion time. Thank you for the attention.